Good afternoon to everybody. On behalf of Department of Mechanical Engineering, Christian College of Engineering and Technology, Bhilai, Dr. R.H. Gajghat, welcome you all in today's afternoon session of 1 week faculty development program on 3D printing and design, organized by Department of Mechanical Engineering, Christian College of Engineering and Technology, Bhilai, sponsored and funded by AICT under AICT Training and Learning ATAL scheme. Today's invited speaker for this session is Dr. Y. Ravikumar from NIT Warangal, who has already joined with us. Welcome you, sir. Sir has already delivered one lecture on applications of 3D printing in aviation industry yesterday. So now, without taking much time, I will request to Dr. Y. Ravikumar. Sir, please continue your session. Word to you, sir.
Yeah.
Hello.
Hello. Yeah. Am I audible, sir?
Yes, sir.
Yeah. Very good afternoon. So thank you for your introduction to the participants. So let me share my screen, sir, first. My screen is visible, sir?
Yes, sir. Yeah.
Thank you. Yeah, very good afternoon, one and all. The topic for this session is on rapid tooling industrial applications of 3D printing. So this is the one of the applications of 3D printing. So that too, it is in say the tooling application, means how you are going to make the molds or the patterns for the either it may be for injection molding or for die casting or the sand casting applications for any one of these applications. So how we are able to integrate the 3D printing technology, especially for tool making industry. So actually, this is the my agenda of my presentation. So let us see how this 3D printing technology is in the manufacturing scenario. Though this technology started with prototyping applications, now it has went to the maturity levels of in making end usage products, even the tools just now we are going to see. So then we'll see the impact of this 3D printing in manufacturing as such, right from the inception, maybe for the past 31 years. This will be, and then 3D printing applications, say, will be the other topic which I'm going to cover. So the applications, again, not discussing all the applications, but the tooling applications pertaining to tooling applications. And let us quickly see the introduction to this rapid tooling, what is this rapid tooling is all about, and the classification of this tooling methods. So as on date, around say 40 to 45 rapid tooling methods are there. So then we'll see how it has been classified, these rapid tooling methods. And broadly, it has been classified into, say, 4, and then further you have another, say, way of making these tools. But broadly, it is classified into 4 major categories of tooling, that is a direct soft tooling method, indirect soft tooling method, direct hard tooling method, indirect hard tooling method. So we will discuss the under each and every category. So at least say 5 to 6 tooling methods. So you're going to discuss. So the well-known tooling methods under each category we are going to discuss, and the toolless and the patternless processes also, which is the additional to this tooling methods. So this is also we are going to discuss. So predominantly, so it will be the rapid tooling methods, means how you're integrating the 3D printing technology in manufacturing the tools. So either you use as a direct in a single, direct means in a single step you are able to get a tool, means a die or a pattern, or even it could be an indirect method, means maybe at least two say steps it may continue say complete to make a tool. So it may be an indirect method, or it could be a soft tool, means like it may be say the life of the tool may be limited. Why? Because that is by the material that you are making the tool properly. So that may limit you in a certain number, a dozen number maximum, or a few dozens, but not more than that. So and the hard is like the name sounds that so the tool life may be you can make use of these tools for say um, lasting for say 1,000 or more than 1,000 the parts that you can say get it from this tool. Maybe that is the hard tool. Then we'll explore this the various tooling methods. And say before we get into the tooling methods, then let us see this 3D printing, how it has been impacted the manufacturing scenario. So the 3D printing in manufacturing, so it goes to a story of say transformative value. So what do you mean by this is say a simple example, like we have say the uh, the television. We got the television. The invention of television has not say stopped the radio, or not stopped the say movies, right? So but you have the television is existing, the radio is existing, the movies also as well. These all three are existing, but so it is not so destroying, the one invention is not destroying the other one. So but it may even so transforming, so some kind of a transformative value has been added for each and every invention, right? So similarly, if you see the 3D printing in manufacturing, how it got evolved, or how it has been transformed, transformed the value, or so each invention, so it may it has opened the new opportunity, say not say disappearing the previous invention, absolutely not. Like it is opening a new doors or the new opportunities in each and every say wave. So you can say the 5 waves it has come, the 3D printing. So as we know that the first wave, or the first say invention was like a rapid prototyping. As we know that this technology used to call as a rapid prototyping. So where the idea of invention of this rapid prototyping, so it has changed the expectations say regarding your design iterations. So previous to the rapid prototyping, so we used to use only the conventional methods to make even a prototype. It may be a single prototype, maybe single part, or maybe a few number, but it has to undergo the um, as well, like how many parts, irrespective of the number of parts, like which we need to, in a conventionally people used to say undergo that much effort, even though it is a single part or maybe a few number of parts using for a prototype. But the rapid prototyping has changed the scenario. So it has say come out with a lower cost of production for your prototype. And so it has even the most important thing here is the faster time to product. So this is the it has changed the scenario of fabricating the prototypes. So with the invention of rapid prototyping, so that was the first wave, which we can see that it has opened the doors for making the prototypes at the faster phase, or without the what you call your the lead time. So you are having a lesser lead time. You could able to even introduce your product into market by quickly making the prototype. Otherwise, you don't have a luxury even to wait to fabricate the prototype if it is taking say months together. But it is not going to do good to the company. Why? Because you have an idea, and your competitor should not catch up that idea and introducing much earlier than to into the market. So that is what where your rapid prototyping has changed the scenario of making the prototype with the say lesser lead time. So that was the first wave of the invention in this direction. And the second wave, so it was the indirect manufacturing. So what do you mean by indirect manufacturing is exactly the rapid tooling that we are going to discuss now. So the indirect manufacturing says like either you make a master pattern with this technology, or you can make a tool, means like it may be a mold or a die for your say injection molding or die casting applications. So that you're making these either a master patterns or the tools. So those are getting fabricated through 3D printing. Means um, even though you are not manufacturing directly, but definitely you are doing a indirect manufacturing here with producing the patterns or the tools with the 3D printing technology. So that was the second wave where our discussion, today's discussion, will rightly fit to this second wave. Means where people have started with the polymer printing. So the rapid prototyping scenario, if you see that it was say late 80s and early 90s, this technology was started, and you have only the polymer was the material used to make these prototypes. But that was not explored by the other engineering materials like metals, ceramics, or the composites, or the functionally graded materials. Now you are enjoying that materials in 3D printing, but that was not there earlier. Then people realized that to bridge that material limitation gap, and then people are started integrating this technology with the indirect manufacturing, otherwise called as rapid tooling. So that is the second wave, where our point of discussion will rightly fit it here. And see the third wave. The third wave is the custom manufacturing. So the custom manufacturing, so that is say it is not only customizing the product, it also addressing more complex individual products. So say the otherwise normally you may come across in medical application, this is quite often, or even consumer products or some extent. So you want to personalize the product, or otherwise you call as a bespoke designs or a bespoke innovation. Means so that is particular to a user, or a patient. If it is a medical application, so it may be particular to that patient. So the patient specific prosthetic, or the patient specific device, or the patient specific implant in medical, if you talk about, or nowadays these bespoke innovations, so even gaining a lot of attention in the recent times. So also why? Because you have a lot of mass customization, so where it will exactly fit to this say third wave, means where you have a customized manufacturing scenario. So this is gaining a lot in the recent times, not the say mass production has been say outdated, but now it has mass customization. So you can customize your manufacturing process. So by with this 3D printing technology, so based on the individualization of the products, that is through either a 3D scanning technology which you are going to scan, or even it could be a bespoke kind of input. So that is a user specific, or the customer specific say requirements. So you have the third opportunity where with the doors has opened for say custom manufacturing, and the personalization, individualization. So that was the opportunity through the third wave. And coming to the fourth wave, so the fourth wave is the complex manufacturing. So complex manufacturing, so which uses this 3D printing technology, so with an advanced material. So this is what, where, as I already mentioned, so it was those started with the polymers, but now it has been extended to say metal alloys, super alloys like Inconel, or say titanium, aluminum, say alloys, or even it could be a smart materials. Now even it could be a smart material, or hydrogels, or even it could be a functionally graded materials, or even it could be a electronic materials. So you have a lot of say advanced materials that has been integrated with the 3D printing so technology, so which ultimately creates a specialized or a custom final parts in a low volume. But as we know that it is not meant for a mass production, as we know that. So it is initially say targeted to the low volume production, where you have a lot of complexity in the products, and then using the multiple material structures, or the advanced materials, so that has been integrated or that has been say added to the say feathers to the 3D printing technology. So that was the fourth wave. And coming to the fifth wave, or the recent developments, so then that may be the 3D production. So with this fifth wave or the 3D production, so you could able to say simultaneously reduce the number of components. So I hope this we have already discussed in the previous class, in the session on the aviation, or even in general any 3D printing designs. So how you are going to get the benefit with the compared to the traditional designs. So where you can simultaneously reduce the number of components, that is the part consolidation, or the part count can be reduced with this technology. And it also reduces the part weight. So that is through with the bionic designs or topology optimized structures. So where you could even be able to reduce the part weight of the product, and it will also simplifies the design, say and it also reduces the product development time, of course. So that is always there. The product development time has been reduced with this 3D printing technology, and it also improves the part performance and the functionality. So this is what the take home message here is, like say not only it is reducing the weight, and not only it is reducing the number of components, or it is simplifying the design, and it is also compressing the time, and it is also improving the performance of the existing system and the functionality of the existing system. So Our point of discussion today is the second wave, that is indirect manufacturing. So that is otherwise called as a rapid tooling. So then let us quickly see this 3D printing application. So where our tooling application will fit. So that is my intention, to keep a couple of slides here to understand the importance of this tooling application in 3D printing. So we have the design applications. Probably this is the initial level of the application, but we cannot say underestimate the each and every application, as we are even understood from the previous slide, that the first wave has given us the rapid prototyping application as the coined theme, and the second was tooling, and the third was say a customization kind of a thing, and fourth was thrown as the complexity, and that sort, and of course fifth was like the 3D production. So but it will have now prototyping applications is also say coming in a it is not suppressed by the latest applications or the latest developments, but still you have a lot of applications in the design space, like you talk about the design related applications. Maybe it is a CAD model verification, just using for the CAD model verification, or the checking with the design specifications. So that is always there for one of the applications of your 3D printing in design, and visualization of the objects, and the proof of the concept kind of a thing. You want to say test the proof of you want to prove the functionality, or the proof of that concept, that is at the very beginning stage of your design. So this 3D printing is also a prominent application, and marketing and presentation models. So that this is some of the design applications, and of course engineering analysis and planning applications. So which we need to perform, say evaluating the form and the fitment of the say the assembly or the product. So then we are going to make a certain form verification models or the fitment models to do that sort of analysis. Or sometimes you do use a flow analysis for these models. You use it as a flow analysis, so for testing the functionality or the flowability, or things like that. So so in that way, where you have so that sort of thing. Um, so in our engineering applications, even analysis of the stress distributions. Even further, you may do with the packages, but further even you can 3D print them in different colors and analyze the stress distributions. Even that can be also done by using this 3D printing technology, and some pre-series parts can also be done before you go for the actual production. So then pre-series parts can also be a few dozens of the parts can also be done. And then diagnostic and pre-surgical operation planning. So it is in the medical domain application, where you can very well say use this model to diagnose the disease of the patient, or you can very well plan the surgery. So means the surgeon can very well plan the surgery before he goes into the operation theater. So you can very well plan that what sort of say the instruments, the medical instruments or the medical devices he or she has to carry, or even intraoperatively they can take these models into the operation theater, and intraoperatively they can work on those models, sterilize them and use it inside the operation theater. And even design and fabrication of custom prosthetics and implants. So this is this is well in the third wave, where you have the customization, a lot of customization that has opened the doors to do this kind of applications. So, and then anyway, you have several design, engineering, analysis, planning applications. And then what about manufacturing and tooling applications, where our discussion, today's discussion will be focusing here in this area. So that is a manufacturing and say tooling applications. So tooling, mold parts, just we even understood, like you have a 4 broad categories. So we will explore this: what is direct soft, indirect soft, direct hard, and indirect hard. And apart from this, and you have the casting applications. Even you can integrate this with the sand casting applications, or investment casting applications. So you may get doubt, how, sir? How means, like, you can make a pattern, master pattern, to prepare a mold for your sand casting, or you can make the wax patterns, or any sacrificial patterns, so that will be integrated with your conventional investment casting procedures. And even you can use the evaporative pattern castings, so such kind of a sacrificial kind of patterns that can be used in this casting applications, or even die casting applications. You can make a die for your die casting applications, or EDM electrodes, or master models. So you can say this is the area where we are going to further explore this tooling part, especially. And industry wise, even we have covered aerospace industry in the previous session, and I hope other speakers so might have covered the other applications. But anyway, you have a huge potential. Say the major industries. The 3D printing technology is say you know, the kind of what you call, it is more prominent or more suitable, this technology, as far as suitability is concerned. So it can be even suitable to any industry, particularly where you have a digital data with you. But how do you justify, means, like, we have discussed some unique capabilities of this 3D printing technology. So that unique capabilities may much inclined towards some of the industries, and those industries also playing a vital role, like aerospace, automobile, your biomedical applications, jewelry, coin industry, tableware, consumer electronics, home appliances, etc. So if you see the industry wise, it may be and if you see the nature, the manufacturing or tooling nature of the application, where we are going to explore it. But if you see, so that tooling may be used in your aerospace application, or automobile application, or even biomedical applications, so, or even a jewelry applications, where we are going to make some say some wax pattern for your castings, the jewelry casts. So very well, you can use this tooling technique. So by using a 3D printing method as a manufacturing of these tools, so you can very well do that. So we'll discuss in length about this. So, and then coming to the if see how these 3D printed parts has been used in which purposes, like say you can see the market share, or the percentage of usage of these parts, how you are making use of these 3D printed parts. So the majority goes to the functional models. So the functional model means, as we know that it is like almost a similar material that you are going to use for your final part. Means then only you can correlate your models, these functional models, with the original product, how it behaves. Means it should be the exact material, or it may be the close properties or the characteristics of that the model versus your actual product. So then one can understand this figure will tell you the story, how this technology got matured in terms of preparing a functional models, not the prototype models, though it was like started with prototyping applications, but now it has been say the majority share goes to the functional models. Means the technology has say matured enough to produce a functional models. So that will tell you the story. And of course, you may have 15.3% as a visual aids for engineers. So just for the visualization purpose, probably these parts or the models has been used. And some 12.1% is the fitment and the application, a fit and application kind of applications, like where we need to test the fitment or the assembly, the fitments and the assembly purposes. You have that models around 12.1%, and 11.7% rapid manufacturing. Means that is direct usage, end usage of the parts. So even we discussed in the previous session with the aviation industry, how they are using a fuel nozzle that has been used in a say aircraft, so aircraft engine. So aircraft engine parts or even a medical applications, the implants or the automobile, say engine blocks or intake or exhaust manifolds, all that, or say rapidly manufactured, and it has been used for end usage also. So that will tell you the story. And then 9.9%, it is the patterns for metal castings. So that is quite up to our discussion. Like say you're talking about the rapid tooling, so it will comes under the indirect rapid tooling method. Means you are producing a master patterns through this technology, and further that master pattern as used to prepare a mold, and then you are getting a metal casting out of that mold. So you have such a applications around 9.9%, and another 9.9% patterns for prototype tooling. So for prototype tooling purposes, so 9.9% the used for this purpose, and 8.9 is presentation models, so just for the presentation applications and tooling components. So this is the our point of discussion, like where you are able to make the tooling components, a die or a mold, die insert or a mold can be produced. Your tooling components is 4.7%, and ergonomic studies, like say, which you can use some of the models for the ergonomic studies. And then visual aids for tool makers, maybe 2.4%, and 1.7% fixers and manufacturing aids, and other 3.2. So, what is the conclusion from this statistics saying that the functional models that will tell you the good direction that this technology is going, and rapid manufacturing, you have a good enough contribution, and of course, tooling applications like either patterns for metals, patterns for prototyping, or tooling components, where you have 9.9 plus 9.9 plus 4.7 exclusively for rapid tooling applications. So this statistics and the applications and the importance of this 3D printing in tooling. So let us see what is a rapid tooling technology. So let us see this rapid tooling. So what is the necessity of going for rapid tooling? What is rapid tooling? So rapid prototyping was the technique, as we know that, and then it was the first wave that we have discussed in the previous slides also. And it has a limited range of materials, where it was started only with the polymers that we know. And then majority of the times in the initial days, it used to use for only visualization and dimensional and geometric verification applications only. The design very beginning just for visualization, dimensional checking, geometry verification they used to use. But just now we have seen from the whole statistics, you have a functional models, so that is gaining a lot of attention. So you have the functional testing of these prototypes, so it is oftenly not done before this tooling. But due to this different properties of your prototype with the production parts, so the initial that is the rapid prototyping technology was unable to support this functional testing of the prototypes. So that is because of the limited materials and the materials that initially it was a polymers, so it could not able to take up the high temperatures and other harsh environments that you may not be able to. But that's the say the root cause people as say migrated to rapid tooling methodology. So the rapid tooling is a method to produce multiple copies of your prototypes, so with functional materials, so which that properties in a very short lead time. So you are going to get the lead time advantage here, and of course complexity is also free, as we know that. And then you're going to produce a multiple copies, not people has the mindset this technology this is only for meant for a prototyping, means maybe one part, maybe limited parts. But if you integrate with the tooling techniques, so where you can, once you make a die or once you make a mold, so it can be used for several times, this several shots, so it will be say useful, right? Say, so with that, so the rapid tooling has evolved actually. And of course, not only the functional requirements or the material properties, so even it also say increased mechanical properties and the thermal properties of the materials. So apart from your functionality and your mechanical properties even, so you have an opportunity, so you can add the colors, color dyes, or you can have the more transparent, even 100% transparent materials also available with VAT based system like epoxy resins, which it is 100% transparent materials also possible with 3D printing technology. And even more flexible materials, more opaque or more rigid, all combinations of materials. And that too you can simultaneously say fabricate it. So that is the biggest advantage, which otherwise it may not be possible or a difficulty through a conventional manufacturing method. So that may say lead this tooling application or why we need a tooling say technology. The rapid tooling technology means using 3D printing in fabricating the tools. So that this is the background, so where it has come from. The need for the more materials or the more functional materials or more say mechanical properties improvement and thermal properties improvement. So with that say requirement, so the people has come out or invented this rapid tooling technique. And then this rapid tooling technique is a new technique, as it has been derived from the rapid prototyping. Of course, it was the first wave that we are talking about, and followed by this rapid tooling as a second wave. And then the need was like the faster and the better and the less expensive tooling solutions. So it has been resulted in developing many rapid tooling processes. Like as on date, around 45 tooling methods with commercialized or with the proven tooling methods are available. And even it is either you are using your rapid prototyping or 3D printed models as a pattern, that is the one thing, or which you can create the molds from this master pattern. You can create quickly the molds as quick as you can. And it also uses your RPR2 rapid 3D printing, so to process directly to fabricate the tools. Means, so that's what, like say you are making a pattern and you call that as an indirect way of doing it. Means it should further go to the next step to make the mold, or otherwise you can directly fabricate your tool. So that that is in a limited volume of the prototypes, means not meant for millions, billions, but at least a reasonably a good number, which you can say. So you can make by using these tools that has been directly fabricated through this 3D printing technology. Um, and it often this opportunity to reduce even both the time and the product development, say cost and time, both it has been reduced with this. Otherwise, again, these tools or these patterns, or sometimes you may use it only a single piece. For the single piece also, you have to wait for months together to fabricate this, but that is not going to do a good to under this competitive world, right? Say the product development time should be as low as it is possible. That's what where these technologies are shining. And then this rapid tooling advantages, if you talk, you have a shorter the tooling lead time, as we already discussed, like say your time scales now months to a few days or the few weeks. So now your time frames development of this tool maybe days or maybe a few weeks, but not the months together. And you have a low cost, that is because of the short lead times. And you have the functional testing of the parts, so that is with the early stages of the design. So it will enable us to shorten the lead times and the low cost. It also prefer to produce the parts for functional testing, so that maybe that is at the early stages of the design. So you can even perform the functional tests because of this tooling say applications. And you can directly transfer your parts to the earlier design, so which otherwise if you don't have these models or the prototypes, and there will be a misinterpretation through the drawings, and it may be avoided. So otherwise, if you have a flaw in your design, so that you came to know that that is during the production stage, or after service, or after sales. So during service you came to know that there is a flaw in the say product, or in your design. So then it will cost you a lot to again call back those models, the products that the people has been already used. Oftenly it will happen, right? Say even companies, like big companies, like even automobile companies, or even cell phone industry, sometimes maybe during this batch of the production there is a problem in our thing. They will recall the products, and they will do a free of cost the servicing or replacing. It may quite oftenly, but that may say penalize the not only the profits, but the reputation of your company may also go. But anyway, so you have these kind of technologies which it will enable you to not say committing those mistakes, or with it may give you a right path to run your business. And let us see the classification of this rapid tooling methods. So coming to the classification of this tooling methods, so you have a soft tooling and you have a hard tooling. And again, in the soft tool, the soft tool is the name suggests that, so the tool material may be a soft material, maybe a polymer or a low melting metal, maybe. So your tool has been made with that, you can call that as a soft tool. And then how do you make that tool, whether you're making in a single step through your 3D printing technology? So then you may call that as a direct soft tool. And you are not getting that tool in a single step, but it may be going a two-step process or a three-step process. Then you may call that is a indirect soft. But whereas your tool material somewhat harder, say something like a tool steel or any harder material that you're used to make the tool, and that holds, or that the tool life may be high. So as compared with the soft tools, so the tool life is high. So then that hard tools, either you directly, means in a single step you are going to say make this tool, or in a two-step or in three-step, you can get your tool, that is the indirect hard tool methods. We'll explore each and every say class of this rapid tooling. Yeah, in continuation with the previous discussion, so the soft tools are one, they those are made out of the silicon rubber normally, or epoxy resins, or low melting point alloys, or even a foundry sand. So foundry sand means that is say meant for say sand casting applications. Just you can destroy that mold with a single usage, right? So it means it will tell you the story, means your soft tool may be meant for minimum of a single cast that you are going to use, or it may be a small batch, means so if it is made out of the foundry sand, so it may be a destroyed only single time usage and it has been destroyed, means it's a single cast, or it has been made with a silicon rubber or epoxy resins or low melting point alloys, so it may be holds for a few dozens, maybe 50, 30, 40, or maybe a few dozens, so you can say get out of this tool, means that is a soft tooling technique. And coming to the hard tooling technique, so these are made from the tool steel, which is a harder than the previous material which you are discussing, and of course it may hold for the longer production runs. So the life of the die, or the number of shots that you are going to make use of this tool, it is quite high. That is called as a hard tool. And then coming to the direct, whether you are making in a single step your tool or a die, so that has been created directly with your 3D printing or rapid prototyping process in a single step. Say for example, you have injection molding, or the entire say you have, it consists of the cavity, cores, runners, gating, ejection pins. So everything has been done in a single go, means your entire die setup, the injection mold die setup has been, it includes everything in a single go. It's a direct say a tool. You have a certain methods, not all the methods can be made directly, but certainly you do have a certain processes which can capable of making this direct tooling, say a kind of methods. We'll see that, and some of them are indirect. So the master patterns has been created using that the 3D printed parts. So you are using that as a master pattern. Say for example, you may make a silicon rubber molds, or epoxy resins, or a low melting point metals, or ceramic molds, or created from your masters. So you prepare a master from this, and further you prepare these molds with any one of these materials, means you take a ABS plastic, make as a master pattern, and you produce a silicon rubber mold. So something like that. So you will discuss, we'll explore all these four categories and various 3D printing processes, and how it has been say integrated in these tooling applications. So with this classification, so then we will start with the first category, that is a direct soft tooling method. So the name suggests direct method, means it's a single step you are going to get the tool, but that is in a soft form, means that maybe holds or the lasts for a limited number. Say you may otherwise called as a form tooling, and you have a bridge tooling, but bridge tooling is a bit different. But you may call as a direct, a soft, or otherwise called as a form tools. The direct soft tools, the modeling tool is produced directly. That's what we are talking about. And you have an example, like you have say sand castings. So just you make say sand cores, say with this technology. So then you're going to get only the single cast once you destroy that the sand, the mold, and after pouring your molten liquid in that, and that's basically a single cast you're going to get. Or even you can go with the composite molds, so like you have process like VAT system like SLA, or even say a powder bed system like SLS. So even you can make a composite mold. So for your injection molding with production of plastic parts, so you make use of this composite mold, so that will produce several shots in a plastic parts, that is through injection molding process. Just in a single word, how you are going to make your say tool say directly here. So that may be so made out of the soft material. So you have certain processes here. We are going to discuss these five methods of direct soft tooling methods. So that is from SLS of sand casting and copper polyamide. So this is a composite material, copper, the metal plus polymer, that's a polyamide molds. And then we are going to discuss US direct pruning process. So these are trademarks of the proprietary processes. Those are from so this is from one of the powder bed systems from Germany, that is US, and this is the powder bed. This is the selective laser sintering. This is a US based technology, and this is German technology. And you have a direct aim. This comes from again a VAT based system, so which could directly produce so direct ISS, that is different support styles, and it is meant for injection molds. So the injection molded say the molds can be directly produced by using this method. And you have SL composite tooling. So this is also used to make a direct soft tooling method. And you have 3D printing ceramic shells. It means you can directly make the ceramic shells here, and then you can pour your castings. So your that is from 3D printing, means now it is a binder jetting. It has been renamed by the ASTM as a binder jetting system, and this has been originated from the great MIT University. And then anyway, this has been integrated with the tooling application by making a ceramic shells. But once you know the various 3D printing processes, so how you are able to integrate that here for the tooling applications? That's in a single, say, in a crisp way. What is a rapid tooling is nothing but your 3D printing process, right process and right selection for your tooling application, right? So that's what here. So then we'll talk about this SLS sand casting molds or the sand form. Sand form is a proprietary name or trademark name for the material. The sand form is basically a sand zirconia or the silicon based sand particles. Basically, this is a powder bed system. The material is in a powder granulars, that is either you have a zirconia and the silicon based sand as a material here, and you are going to build that molds, and those cores, the sand cores, sand molds, so they are directly done through the CAD design. So like you are going to design entire die setup in your CAD model itself, and then further it has been printed through the sand molds, and cores has been printed through your 3D printing powder bed system, like selective laser sintering is one of the powder bed system. So you are going to ultimately get a single part. Why? Because this is only the sand core mold, then it is getting destroyed once it got say casted, and it may take 1 to 3 days to complete entire say process. So designing, fabrication, post processing, the semi finished say casting, and then further the finishing it, everything. So it will take 1 to 3 days. And you have normally this is basically an indirect process. Actually indirect in the sense, not the tooling method I am talking about. So this was the uh, what you call the it is not a melting here. The powder particles are not directly melting. The sand particles are not directly melting. So your sand particles are coated with the polymeric binder. So that binder is getting, say, melted rather than, so it will fuse, or it will get the polymer binder is getting bonded the sand grains. So that's what it's going to happen here. So this is a kind of say sintering, or that's what it's called as selective laser sintering. So you are using a laser energy to melt this binder rather than your structure material, that is sand. You have structure material as sand, and the binder has been as a polymeric binder. So where your grains has been say bonded together. So that is in the shape of the mold. In turn, that is the CAD design that you have say modeled. So as for that, it is getting shaped, or it is getting say your the sand core and mold has been prepared in that way. Your sand molds, these cavities are produced or very accurately and have the properties that are identical to your cores through the conventional methods you fabricate, and those are on par with the accuracy as well as the other properties that you try to say do it. It's on par with the conventional methods, but you're going to get the advantage of, say, the time scale in days, but not in weeks or months in a conventional methods. Normally, you adopt this through a conventional tooling method, and these are used for sand casting applications, right? And then you have the functional prototypes can be produced, and also it will modify if necessary a new product within the few days. You have always that flexibility through this method. And this is one of the example, like where it has been so the sand core has been printed through this process, and which you can see how complex the sand core, the conventionally making it, so then how tedious it's going to be. Then it will be done in the matter of days, maybe 1 or 2 or maximum 3 days. You could be able to complete this even that's what where your this is one of your aircraft engine part, like where you can make these sand cores, and further it has been, say, casted into metal, maybe aluminum kind of material, that you can even say get the part ultimately into that aluminum material. So, and then even you can make use of the composite, like a copper plus polyamide. So you, through this SLS tooling, that is a direct soft tooling with composites of copper plus polyamide. So you have the copper plus polyamide. It's a new metal plastic composites, and which is designed for the short run production applications. So now it is meant for, say, minimum 20 and maximum 150 parts. So your so tool life will be, so you can it will be done in a 1 week span, the development time, and no furnace cycle is required here, and your unfinished tool inserts can be produced in a single day. So and further you do and include the designing, post processing, everything. It will take one week, but you can directly within 1 day you can able to produce your unfinished tool. And during your CAD stage itself, you include all the cooling lines, your shelling design, and then your ejector pins, guides, gates, runners. So include everything in your CAD design itself. So in a single step from CAD to the tool. So that's the idea here. To rapid tooling means that's the CAD to the tool you are going to get in a single step. So, and then you have these inserts. The surface is finished with sandpaper. Why? Because you may be you need definitely a mirror kind of a finish for these tools. Then obviously you cannot get a mirror finish through a 3D printing technology. Then definitely we need to do a certain post-processing, super finishing methods to enhance your, say, the surface finish of the molds to a mirror finish kind of things. So then you can do that. And of course, you do a backfilling of the metal alloy to improve the strength of the mold. That is also done. I will show you some of the case studies like how it has been done. And then you have these inserts are produced through a copper polyamide, which is easy to machine and easy to finish. Like we can easily use your the post-processing methods to finish this die. And their the heat resistance and thermal conductivity is also better more than the plastic tooling. So this is a composite of metal plus plastic. So you have now the advantage of increased heat resistance and thermal conductivity. So if you compare with an ordinary plastic tooling material. Yeah, and this is what I'm talking about. Say you have the entire setup in in your say die design itself. In a CAD model itself, you include your cooling line, and you have a ejection pin guides, and this is you have the back surface of the your insert, and you see the working surface, so which it has a runner gates and everything has been included. So this is the working surface, and this is the back surface of your say insert, and these are the parts that has been produced through this say mold. So you can see these parts has been produced by making use of this say insert. So in this way, you can directly produce your entire die setup from the CAD to the say tool in a single step, and then you integrate to with your say injection molding or say die casting or whatever it is. Like say you can integrate this to your conventional methods. So, and then you have the other technique here is direct crowning. So, but it is almost similar to the previous technology, but only you have, this is a German technology, but it works with the same principle. But there was a fight between these two people. But anyway, now they had a settlement, or they had compromised, but there is a slight difference in the process, but almost it looks same. You have a sand, say the sand particles, the powder, in a the sand granulars has been taken the same like the previous one, and you have the sand casting molds, and the cores is directly sintered. Again, you have a resin coated foundry sand. This is here, but they have a different proprietary name, but it works with the same principle. Nothing is different much here. So your molds and cores has been produced with a single part. Why? Because it is a say sand core mold. The mold and the cores has been produced, and the 1 to 3 days. So yeah, this is the core, the sand core they have produced through this process, and further it has been casted. So this is a core cylinder. So they have produced 3-cylinder say engine for the car, and this is what they have done through direct crowning, or this sand core has been produced, and further it has been casted. And you have other yeah, like you have this is the sand foundry sand. It has been used to build the material either in SLS and EOS. So both these SLS is as I said, like this is a US based company, the US based technology, and this is a German based technology, but it works with the same. There won't be much difference, as I already said. So this is the sand cores, and then metal parts has been, and you can find even other practical applications, maybe in the impeller, where you can say produce this sand core to a laser based system, just now we discussed, and then further it has been casted. And this is the hydraulic controller, the central block, the core, sand core has been produced, and further it has been used for the casting. of the metal parts. And you have the steering block for a car. The steering block, this is the core, sand core, and this is the casting that has been come out of from this say core, the sand core, and the metal casting that has come out from this automobile, one of the automobile applications. Either it may be automobile application or any machinery applications like impellers or any hydraulic controllers. So we can quickly produce this, right? It's a matter of days. Otherwise, traditionally, conventionally, it used to take months together to develop this sort of tools. And this is again a sand say core, and further it has been casted in aluminum, say 356 D6. So it's aluminum. So it has been come out from this sand core to the casting. And you have another technology called voxel jet. Voxel jet, this comes under a binder jetting system. I hope you have already aware of a binder jetting technology in 3D printing. So binder jetting, so far we are discussing that is a laser-based powder bed system. That is either your SLS or EOS. It basically comes under a powder bed system. But you have a binder jetting system. So where you are going to jet the binder onto the powder particles. So then this is a voxel jet technology which produces the sand cores and the mold packages. But the technology used is different here. But the workflow remains same. Like so you start with CAD model, that CAD setup. So it consists of the entire dies, the die, a complete die setup or design, and then further it has been printed in a sand core, and then it remains same. But you have a very big size components here, like it may be 4 meter by 2 meter by 1 meter. So that is the huge 4 meter. That's a big sized components can be produced here. So you have a big dies. So the tools which you can directly produce it. So the materials typically use it here as the quartz, sand, or furan resin with molds and casting properties, which is compared with the customized solutions. And you have you have another company X1, but X1 voxel jet, all these are a commercial companies, and where the MIT University has sold the patents to different companies or different regions in US, in Europe. They sold these patents. So another one is an X1. X1 is also works with the same binder jetting technology. So for your industrial materials, so which you have this you have the build volumes here also, say around 1800 by 1000 by 700 build volume, and build speeds around say 60,000 to 85,000 centimeter cube per hour. So it's a huge speed. It's a multi-jet, jetting with the binders, and it is a bit faster. Even it can be further improved because the speed is further, it should be improved. But this is the typical speed that you're going to get in the say the present scenario. The layer thickness may be around 0.28 to 0.5 mm. In the print resolution 0.1 mm by 0.1 mm. So you have these machines, the big size machines, which you can see. This will be the size of the bed, like it may be a 4 meter by, or say 3 meter by 1 meter. This will be the sand will be, it will be loaded and it will be say done here. The process basically works with the binder jetting principle. And you have other technology called a direct aim. So direct aim, it has been developed from the Dazzle and the Berist, and this is meant for producing 20 to 100 parts, a minimum 20 and maximum 100 parts. And primarily, it has been used the VAT-based SLA system, the stereolithography operator system. So as we know that VAT-based system will produce a resin-based material. It's a resin, photosensitive polymer resin. So which it allows directly producing this injection so thermoplastic, the injection molding parts. So these injection molding parts, so they have a different build style here for not the models they use in a routine application, but they have a dedicated, say, toolpaths or the support structures they have for the injection molding applications. So they developed exclusively this technology for uh, injection molding, preparing the injection molds, and it produces high level of accuracy. So one of the biggest advantage of VAT-based system, you will get the best of the best surface finish in polymers among all the 3D printing technologies, and that's what where you're going to get the advantage here. And build times is also, this method is relatively slow. That is the negative side here. The build speed is not that much great, and the mechanical properties also not that much great. But it's a very low, and the tool damage can occur during the ejection of the parts. And this is more evident when you are using a geometrically more complex parts. So and these modes, but you have but quickly you can produce, but the you have the negative sides of these things. But the one is a builder, but the best of the best part is accuracy, maybe very high. And you have the direct aim process. Again, it should start with the 3D mold design, and further it has been done through your machine, the SLA based machine. This is a thing, and which you're designing everything. You have the cavity core, so everything you have designed in the CAD model, and it is getting printed here. And now you are as we already discussed, like say you are going to backfill your, so this is the backside of your say you add the cooling say lines, and you backfill with the mold. This is not a working surface of the mold, it's a backside, but you do a backfilling of this mold with the epoxy resin and further, and you do finally you have the the cavity and the mold, and you have the part which has come out from this injection molding thing. And even you can see the other applications of this injection molding, say the mold setups, so which you can directly produce these, or the say the two cavity mold sets has been produced through this is done through a material jetting, that's a polyjet technology, the material jetting system. So it has been developed, but these are the base plates, and which it has been, say these are the getting printed through a polymer, the polyjet technology, and it has been say fixed into this say your ejector pins and the entire setup. So we can make use of this and now you have so far we have discussed the direct soft, but coming to the indirect soft means you're not getting in a single step this mold, so then you may be getting it in say 2 steps or 3 steps that we'll see. The indirect soft tooling um, is the method to produce a master patterns initially, and it has been used to replicate your mold. So that is either one of these materials which you can use a rubber, epoxy, or low melting point. We will see one by one. You have several technologies, but I picked only the well-known, say, indirect soft tooling methods. Like say, you have a spray metal tooling is a one, and silicon rubber molds. This is very famous for an automobile applications. So it has been used by several automobile companies to integrate this technology into their automobile applications. And you have epoxy tools and spin casting with vulcanized rubber molds, castable resins, and plaster molds, and of course casting, investment casting, die casting, spin casting, and sand casting. So you can we'll see one by one these technologies, but it will a indirect soft tooling. The name suggests. So you are going to make the pattern, master pattern, out of your 3D printing technology. So why? Because it's an indirect method. So initially you are producing this master pattern. So this master pattern now, in order to improve the working surface area, so like where the heat resistance and the characteristics that you are looking at, then you use a metal spray gun. You have a metal spray shell has been coated onto top of this the master pattern, and now you fill with the 85% aluminum fillets. So you fill it, and this is the half of the mold, and you have turn on the other side and do it for the other part of the say die. So you again you put that the splitted pattern, the other half, and then you spray it, metal spray it on it, and then finally, so you have, then you pour this resin, and finally you have left out with your mold then that cavity. So then you can make use of this for your say application to use it. So you have the other well-known say automobile application, where you can find this um, not only automobile, even you can find for any machinery, machine tools, that you can find these lights or the cases for your headlamps or the tail lamps of your automobile applications, where you can find this is a silicon rubber molds has been used. So you are going to produce the master pattern through the say through your 3D printing technology. So you make this say master pattern here. So this master pattern made, and then you use a vacuum chamber here. Probably you may come across your this vacuum casting technique. So you have the vacuum chamber inside, and you have the silicon slurry. So you have the sprues and then the mold box, and you pour it and allow it for the solidified this silicon rubber, the silicon slurry, and then you say cut this rubber mold into two halves and remove the pattern, and now you have that mold, and now you mix your material. Like you have the resin A and resin B, and we can add some dyes also here to get the different colors. So then now you stir it, and then you support it into the mold and allow it for solidification, and now you cut that the parting line, and now you have a final say part has been come out. So then in this way you prepare the master say master pattern and prepare a rubber mold, and then you cast it, you add the dies, get a different colors, and you cast it and you get your parts. So you can use it for maybe a few dozens, maybe 100, 150, and again depends like the geometry and other factors. So then the life may change here and there. But so in this way, where you can make use of this technology, yeah, and this may be the same, but it has shown in a different version. But anyway, you have the master pattern and put it in a box, and then you pour it. You make a rubber mold and cut it, and add it, and you put it again. You say finally after the solidification, you cut this the parting line, and then you got your part. So, and you have the castings, so you can go with this metal molds. So you have investment casting, die casting, spin casting, sand casting. So these metal molds so are generated the very time consuming and more expensive. So if you go to machining, conventional machining, But if you combine this with 3D printing, and where you have the even you have some zinc aluminum alloy molds can be rapidly made through this technology. And this investment casting, as we know that we need to have a sacrificial model. So you can nowadays the material, the sacrificial materials, each and every 3D printing machine can say accommodate either in terms of a wax or a foam or a paper or a polycarbonate. This will act as a sacrificial patterns, so that you can directly produce any complex geometries through your 3D printing or rapid prototyping, whatever you call. And you can use that for your investment casting applications. Say you use this as a sacrificial models and prepare the molds, and then you cast it. So the investment casting, and when we so every machine, so it will support, maybe you can go with a sheet based technology or powder based technology or extrusion based technology or a binder jetting technology. Almost all the processes it will support, so you can find any one of the sacrificial nature of the material that will support all these 3D printing processes. And say, as we know that the investment casting process, but only one thing which you have done is, so you have made this say patterns, so the wax patterns or the sacrificial patterns through 3D printing, and then rest will be same, like you prepare a tree, and then you apply the slurry, and then you heat it, evacuate it, and then you cast the the molten metal into this cavity, and then allow it for solidification and break it, and then take out your part and do finish, and you will get your metal part. I'd say you can see this is a one of the automobile application. This the cylinder head. So this is the pattern, the sacrificial pattern. It has been produced through additive manufacturing, and then further it has been casted. So this is the casting, so which you can directly use this for your automobile application, and it may be an aerospace application or any say automobile application to get some wiper motor casing, or things like that. You can even use some impellers, so even it could be some metal screws or the implants for medical applications, so say impellers. So you can make these sacrificial say kind of uh, patterns, and then further you cast it in investment process. So you can generate your objects through 3D printing, which utilizes the indirectly into an investment casting process, which you can be able to make a master pattern for creating the silicon rubber molds, or which can be even employed for a small lot of wax patterns that can be produced through with that. And you have SLA models, so it can also be used to make the silicon rubber molds used as a master pattern, or even last patterns has been made to pour the wax into a silicon rubber molds. Or even you can go with the die casting applications. A similar way, say to ceramic tools can be made, and it is possible even to fabricate ceramic molds to cast a metal alloy. So that is your die casting applications. So can also be done through this. Your ceramic molds has been behaving like a die cast molds, and it will be used to fabricate one metal only. That is the thing. And then you have the next class of tooling method is a direct hot. The name suggests like you're going to get it directly, and it's going to be the hard tool, means the tool life may be high. So coming to the direct hot tooling, so but you have in the previous indirect tooling methods, you need to have minimum one intermediate replication process, means from master pattern to mold. that is minimum to minimum. It requires one intermediate step to complete your tool. But here you can directly get your tool in a single step. So you have the um, but anyway, so if you are going with the multiple steps, definitely your error may accumulate. If there is error in your any one of these steps that you are coming from the master pattern to replication of your mold to the casting, and then there will be a chance to losing of your accuracy. But you can have an opportunity here, the direct tooling method. So you can directly produce the injection molding or die casting inserts. So that is from CAD to the die insert for your application, like injection molding, a die casting, or anything for that matter. So then you can use the applications as a prototyping or a pre-production tooling, or even production tooling parts also can be made through this. And coming to this direct hot tooling, so you have this. So this is a very interesting and recent developments. That a lot of research is going on in this hot tooling methods. And you have the biggest advantage of hot tooling is faster turnover times, and which creates the highly complex shapes, molds, the high volume productions. So that is the, you can use your tool for a good number of shots. So then you have a high volume production here than the previous technique. So you have these inserts for pre-production or production tools, like you have US direct tool or direct metal or DTM, and again you have two German and US companies here, but works with almost similar technology, and sheet-based LOM tooling and Pro Metal um, is again a binder jetting system here, and laser engineered net shaping. This is a DED system. So it means altogether you need to produce the hard direct tool, means it should a high melting point metal, maybe hard tool steel or the substitute materials somewhat closer to that. So then you may use this direct hot tooling process. Then we'll talk about the US technology. So this is meant for producing the inserts for injection molding, blow molding, die casting molds, and sheet metal forming. Deep drawing dies can also be made directly, or even direct parts can also be done. So they do have a certain material. The powder material may be a direct steel 50 or a direct metal 50 or direct metal 100. Means there is a slight composition, and the size of the powder particles maybe here designates the 50 micron or 100 micron, and even composition is also slightly varied. So you have a bronze based or a steel based powders. So where the bronze based powders, so which has been sintered, means you have the binder has been coated with organic resin, binder has been coated, and this typically it produces a 90% dense part, and further it has been infiltrated to get 100% dense parts. So it should a bit infiltration should be done here. So this is the one limitation, or you have to go with the infiltration. It is not required, sorry. So infiltration is not required here to go with a steel powder, but you what kind of whether you are going with a steel or a metal, so then that matters. So then you can directly produce this say die tooling assembly, this entire thing. This is the base the and then these are the inserts that has been produced through this 3D printing technology, and now directly it has been assembled and it has been integrated with the injection molding machine, and where you can get these plastic parts from this die. So this die, the entire tool assembly um, with the base plate and the ejection pins, everything, and this has been done through additive manufacturing. This is from the direct US tooling, and this is another die, say die setups that has been produced, and then from that die, these are the parts, the plastic parts that has been come out, and even the conformal cooling channels. So this is the another advantage, added advantage with the 3D printing technology, where you can confine your cooling channels. That is the shape of the object that you're producing it. And you have several say case studies of this nature. Like you can you imagine that these inserts has been directly produced through um, uh, metal 3D printers, like the DMLS or any powder-based metal systems. So, and these are the dies, and these are the parts that has come out from the maybe a die casting die. It has been produced, and the parts and these also big sized dies has been produced through this technology. And you have blow molding, say dies can also be done through, and this, some of the stamping dies. And you have direct parts, a impeller or some instruments. These are directly produced. And the rapid tool process, you have two different processes here: rapid steel 1 and rapid steel 2. And there is a slight difference between 1 and 2, but basically you are going to get a green part initially, and here the the mean size of the powder particle is 55 microns, and the green part has been initially produced. And then you are using a binder, thermoset binder coating, so which will be putting it in a furnace to cross linking of that. And then finally you do a furnace processing to fully dense your part to 100% dense by mixing it to copper, to infiltrating it. So means ultimately your tool is a 60% steel and 40% copper, and it's a fully dense, and it has been say finished with the surface grinding and milling and drilling, EDM and polishing and surface plating. You do come with a mirror finish things by performing this, by post processing this. And you have yeah, this is it for the workflow. Like you start with CAD model and prepare this say the green part, and then you have the polymer plus that infiltration drying has been done in the furnace, and debinding has done, and sintering and infiltration, and finally you are going to get your insert and been finished after post processing, and it has been used for the injection molding. These are the parts it is getting printed. So, and you have other say these are the dies and the parts has been produced. Dies and the parts has been produced with rapid steel 1 and 2 and 1. There is a slight difference. You have a different temperatures and the different infiltrants you are going to use here, but it have the green part, brown part, and then followed by infiltration 2 hours in the room temperature, and the temperature raised to 1050 degrees C. And this is the furnace treatment should be done. And you have LOM process. It is a sheet lamination based technology, where you have the binder coating, and the polymer sheets has been coated. You have the glass plus ceramic fibers plus polymeric binder has been coated onto these sheets, or even either you use a polymer sheets or ceramic sheets. See, you have the silicon carbide ceramics plus the polymeric binder as used as a material to prepare these tools. And the pro metal, it is a Irish technology. So again, it has come from the MIT. This is a binder jetting based technology, and you have better properties of the tools, which it can withstand up to 200 MPa, and it can holds for say 1 lakh um, 1 lakh shots with your glass filled nylon. So you have the last classification, the last method here is the indirect hot tooling. So the name suggests it's the indirect, and a hot means like you have at least one intermediate step, and then you have the hot tool that you're going to get here. So you have a numerous indirect RP tooling methods here, but you have continuous growth in this category. Then these process remains, say, a small differences. Like you have a 3D Cal tool is a one of the well known under this indirect hot tooling, and cast aluminum, so zinc tooling, and EDM electrodes, echo tools. So 3D Kel tool, this is based on the metal sintering process, and it converts your master pattern into a production tool insert with very good surface finish. And this insert and built into two materials, it's the stellate or A6 composite tool steel. And this process has 6 steps, like fabricating the master pattern initially and prepare a RTV tool, and filling the RTV tool with your metal mixer, that's a powder steel, tungsten carbide, and polymeric binder, and firing it in the green part, and then infiltrating and finishing the core. So these are the 6 steps it will follow, and which you can see this is the die, and these are the parts that has been produced through this 3D Kel tool process. And you have another one is a cast aluminum and zinc tooling, and the cast kickside cavities through a VAT based SLA system has been produced, and it will take 2 to 3 weeks to develop this. And you have very accurate patterns, that is alumina, the zinc based alloy will be used here. And this type is a higher production volumes. It's a more aggressive in polymers that will have high mechanical properties, hardness. And EDM electrodes can also be done through here. The process used here is a powder bed based SLS system. And the last part, anyway, this is the 4 categories, but though you have another process called say a toolless process. What do you mean by toolless processes is, like, say you have this technology in which you have the actual cores and molds are made without any traditional tooling directly by your 3D printing or RP system. So means like you have your 3D printing or additive manufacturing. So you have the indirect method. Just now we have discussed. So you have a master pattern, and then you have the mold and the polygon pattern, and then molding, and then pouring, and finally you're going to get your casted part. So this is indirect, but direct you have direct tool and molding it and pouring it. But you have a toolless process where even it doesn't require any tool, and it will automatically generate your sand mold. So use that sand mold to pour your casting. So you have this is called as a toolless process. And even patternless process can also be, like, say the toolless, just now we have discussed, you have this the you have indirect, direct, and toolless. Or even you can directly make your ceramic shell instead of say making it and then pouring it in there, or directly you can make a ceramic shell. So it has been direct shell process, which is a patternless process. Like, say you have a toolless and you have a patternless also, like where otherwise you come with a direct or indirect method, or it will be a toolless or a patternless, where you can directly produce the shells to pour your casting. So let me summarize what I have done. So presently you have 3D printing or RP systems, or very differ. That's not only in cost and both of these equipments, materials, but also it can capable of very wide range of materials that you can able to process through this say rapid tooling technique will bridge that gap. And you have a wide range of capabilities. Some of the 3D printing process, like powder bed SLS system, you can have a wide range of material capabilities that you can go about. And cost effective systems, like you have nowadays your extrusion based systems are very less costly, and even 3D printing technologies also less costly than any other process you compare. But it's even the cost effective solutions also will be there to integrate your tooling applications. And say if you see the metal casting methods, so the metal casting methods, say you take a sand casting. So for sand casting applications, so the materials that will support, and the processes or the 3D printing process that will support your so producing the patterns or the core boxes. So you have SLA process, you can go with the plastics, and SLS also from the plastics. LOM, you have a paper-based material, it has been coated, and FDM, you have a plastic, thermoplastic, and 3D printing also, that is binder jetting now it is called as in the recent developments. And now you have the plastics can also be done here. And coming to the sand mold, sand cores, you have only the sand supported the powder bed system, and you have a ceramics, so that will be supported through a binder jetting system. So as far as sand molds are concerned, you have only very few, say, choices, but you have the patterns and the core boxes. You may have a good number of choices here for your sand casting applications. And coming to the permanent mold and die casting, so then you have the metallic molds and cores can be prepared. So means it should have the metal facility, right? So means you have the powder bed metal system, or through LOM you have a metal, or even powder bed can also be added here. Then you can even go for the powder bed system to make the metal or the permanent mold or the die castings. Or coming to investment casting, so you have the molds for the last patterns. So you can have a good number of choices with these 3D printing, say, technologies, like go with the SLA, that is a VAT system, or a powder bed, or you can go with the LOM, sheet based or extrusion based, or even the binder jetting system. So you have these many options. But coming to the last patterns, again, you have 1, 2, 3, 4, 5 choices here to go with the last pattern, preparing the last patterns, which are having a good number of, say, choices. And the types of the materials that the your prototypes, like the plastic, wax, sand, metals, etc. So you, depending upon your, say, the available equipment or the facility you have, and the material that is getting supported from your, say, facility, or if not, can it be done through a direct step, or if not, it could be done through an indirect step. So that we have to come out. And then maximal requirement size of the prototype. And another requirement is what is the size. Your build sizes is also another constraints which we need to look for. What is the size of your tool? Based on that, also we need to choose or select an appropriate process. And you have even other things should be considered, as like, say, what is the accuracy of this your prototype, that your resolution, layer thickness, and other considerations which we need to take. And durability of your prototypes in the pattern. What is the life of the tool that you're going to anticipating, that is also should be considered. These are some of the things which we need to consider, and even maximum allowable cost for the budget, or the cost, will also consider here to select your the type of RT method that you are going to adopt. So, okay, I have done from my side, and anyway, these are some of the facilities we have. I have already explained in the previous session. So then, yeah, so I have done from my side. So if you are having any queries,
Yeah, please, participants, if you have, you have any query, you can ask. So thank you very much, sir, for sparing your precious time and sharing your knowledge and experience with us. This session was very interesting and informative. He has given a good knowledge of and information about the rapid tooling industrial applications of 3D printing. I think this session will be very useful for the applicants. Also, I would like to thank all the participants for joining and attending the whole session. Thank you all again. Thank you, sir.
thank you. Thank you for the opportunity given. Yeah, Thank you. Thank you. Thanks to all the participants for your patient listening. Thank you.